All right, so today I will be shilling WebAssembly, which is also known as the fourth language of the web. Anyone know the other three languages? HTML, JavaScript.
.NET.
No. Huh? No, it's HTML, JavaScript, CSS, and now WebAssembly. Yeah. All right. So real quick, what is WebAssembly? Well, first of all, it's not really web and it's not really assembly. I don't know why they call it WebAssembly.
Wait, what?
Okay, here's the official description of what WebAssembly is. WebAssembly, abbreviated Wasm, is a binary instruction format for a stack-based virtual machine. Wasm is designed as a portable compilation target for programming languages, enabling deployment on the web for client and server applications. So if you're like me, when I first came across this paragraph, you're probably like, what the hell is a binary instruction format? What's a stack-based virtual machine? What is a portable compilation target? So here's the previous paragraph, but translated into plain English. So binary instruction format means kind of like a machine code. It's instructions in a binary format. Stack-based means not register-based, meaning when you're writing WebAssembly, you don't think about registers, you think about just the stack. A virtual machine means it does not run directly on hardware. WebAssembly has to go through a runtime to be translated into actual machine code in order to run. For example, WebAssembly has if-else blocks, which clearly wouldn't work that well on hardware because an if-else block can be variable length and you'd have to resolve the branch target and it would just get messy. Yeah.
Could you technically design like an ISA?
Can you elaborate on that?
Like, could you simulate? You make a machine that is running with ISA.
Yeah, people have done that. There's one called Wasm machine, which it's called that because you can run WebAssembly on your washing machine. So it's a Verilog implementation of a Wasm virtual machine. So you can flash it on an FPGA and run Wasm directly on a chip.
What kind of washing machine has an FPGA? I don't want one of those.
Well, what?
I don't want one of those.
All right. And most of y'all probably know what portable means. It means you can run it anywhere. Basically, anywhere you can have a browser, you can run Wasm. Compilation target means you're not really meant to write Wasm directly, although you can. But you can, most of the time, you're going to compile into Wasm through Rust, C, C++. Basically, any language you can compile to Wasm nowadays. Yeah.
Isn't portability a natural compilation?
Basically, yeah. Well, these are just words that came from the previous paragraph. Yeah. So why should you care about WebAssembly? Wasm is being increasingly popular on the web. If you turn off WebAssembly in your browser, you can start to notice a lot of websites that just don't work anymore. Mostly web applications like Figma won't work. Like a lot of really heavy applications, they rely on using WebAssembly in order to bring their performance. I believe it's like a 3x speed up over JavaScript in most use cases. In addition, WebAssembly is increasingly being used to run serverless applications in the cloud as an alternative to like container-based deployments like Docker, which are quite memory intensive and also just in general intensive. Wasm is very, very lightweight. And one thing that's pretty interesting is Wasm is actually being used for blockchain applications. So for example, the blockchain Ethereum is exploring adding a WebAssembly subset as its virtual machine to replace EVM, which is what they have right now. So ETH 2.0, when it rolls out, all of the blockchain applications will be running on WebAssembly. And also, our favorite professor Bovov says it's the SFI of the future. What does that mean? I'm not sure, but yeah. That's a great question. Software fault isolation. Don't worry about it. That's a Bovov word. If you want to impress Bovov, just throw around words like SFI and CFI and RISC-V, and you'll impress him. All right, so one quick demo. I've set up the EM SDK, which is the mscripten SDK. So if we write a world program in C++, so I just wrote a hello world program, and now I'm just going to compile it using EM. Oh, there's not test.cc, this hello.cc. And now if I run a Python server and navigate to hello.html, which port was it? Port 8000. We will see that our program, our C++ program, is now running inside of our browser. So you can compile any C++ program using mscripten and have it run within your browser, have an interface with JavaScript, basically take any program you've ever written. It can run in the browser. Yeah.
Can it run from file scope?
Huh?
Can it run from file scope?
From file scope? Like, can it open files?
No, can you run Wasm from file URI?
I think I'll go over that in a second,
Okay.
but the short answer is not really.
Darn.
Wait, like in the console, like in the
No.
like in the browser, can you just type in hello.wasm and have it run?
No.
What are you talking about?
But so you made a server instead of opening the HTML file.
Oh, right. In this case, it doesn't work because there's some weird CSRF stuff going on in the background.
Oh, okay.
But if you got rid of that security feature, then it would be able to run.
Okay.
Yeah. And there are other ways to run WebAssembly locally without using a browser. And you get the portability benefits, but none of the browser overhead. Yeah.
When you say any program that you can run in the browser, how do you handle I/O and stuff like from devices that aren't?
You'd have to write the bindings yourself, but you could theoretically port it into the browser.
Those are set to isolate certain things, right?
Yeah. So I guess technically multi-threaded applications wouldn't work, but I mean, it's more like it's because we're still working on threads. I think they're in like stage 4 out of 5 right now, so they're coming soon. But a lot of features in WebAssembly are still forthcoming. Yeah.
There WebAssembly runtime in the browser, or is it like filing JavaScript?
There's a WebAssembly runtime in the browser. It's not compiling to JavaScript. Like Safari, Chrome, Firefox, they all basically run WebAssembly directly, or as directly as possible anyway. All right. So now we're just going to dive a little bit deeper into the WebAssembly syntax, the text format. So next time you come across a WebAssembly binary, you can just take a look at it. So for example, if we have a .wasm file, we can look at its contents using wasm to watch. Okay, let me switch over to my remote thick client. Okay, so we have, okay. Okay, so you'll notice that there's quite a bit of stuff here. And that's because mscripten can get a little bit involved. And I don't think this actually fits in my terminal buffer. This is quite a large file. Yeah, so for example, you can see that this file is 151 kilobytes for a simple hello world program. So the reason for that is because in order to run hello world, you have to bind hello world to libc. So including all of the like Wasm libc inside of this binary, which is like one of the pain points of using Wasm right now. However, if you look at here, if you type this to less, if you look for the function main, well, you find out that it's function 53, and then you'd be able to search for function 53. Okay, yeah. Can I pipe this into Vim? No, it won't. I won't let you pipe it into Vim. We're looking for 53. Okay, yeah, then you can actually start looking at, this function's calling function number 13. Let's look at function number 13. Now it's doing some stuff I don't really understand. But most of the time, your Wasm files are gonna look like this, and it's just gonna be really, really annoying. Yeah. Basically, yeah, because that's a great question. I don't think it's possible for it to do that, because it's also not compiling libc while you're compiling your program. Yeah, yeah. I'm not sure. I'd assume you run into a bunch of problems. All right, but that's how you run Wasm to WAT. So in order to look at WebAssembly in the first place, you first have to understand what a stack machine is. So if you all have looked at X86 Assembly, this looks quite different from X86 Assembly. The first difference is that there are no registers. This is a constant I32, a 32-bit integer that has value 5. This is one that has value 1, this is one that has value 2, and at no point do you ever actually push these, you put these in registers. So essentially the way that a stack machine operates is similar to how a postfix calculator from the 80s works. So if you have an expression like 5 minus 1 plus 2, this would actually turn into 5, 1, 2 plus minus. And the way to read this is each number is being pushed onto the stack. So you'd have 5 being pushed, then 1 being pushed, then 2 being pushed. And each operator pops 2 values off the stack and pushes the result onto the stack. So this plus will pop 1 and 2 and push 3. So after this plus executes, we will have a 5 followed by 3 on the stack. Then the minus will calculate 5 minus 3, and we get our result. All right, does that make sense to everyone? So Wasm is the exact same way. We push 5 followed by 1 followed by 2. We add, which pops the 2 and the 1, adds them together. Then we sub, which pops the 3 and the 5 and subtracts them. So at the end of this sequence of code, we will have just the number 3 on the stack. And the stack can only contain I32s and I64s. More on this later. There are no bytes, no words, no buffers, just these 2 types. Although they are changing it, I think, in the next version of WebAssembly when it comes out. There's another way to write WebAssembly, which is using S expressions. Yeah, S expressions, which look like Lisp. And basically, this is the infix to WebAssembly's postfix. We just add more parentheses. So this is subtract 5, subtract from 5, 1 plus 2. Right, so this is the exact same expression as before, but now it has more parentheses. Yeah, so that's basically, this is most of the difficulty from reading WebAssembly, is trying to figure out this stack machine stuff. In addition, there are some quirks of WebAssembly that make it different from a typical machine language that you're reading. For example, there are globals, which are defined at the top of the module. A global can have a mutability, a type, and a default value. You can use get global and set global to modify or retrieve these global values. So for example, get global 0 will take the 0th global and push its value onto the stack. Set global 0 will pop a value off the stack and put it into the global. Right, everyone with me? We also have functions, which are just units of WebAssembly that you can run. You can invoke functions directly from JavaScript, or you can invoke functions from other WebAssembly functions. So for example, this function takes in two i32 values and returns an i32 value, and its implementation simply returns a 0. Basically, at the end of this function's invocation, the return value is just whatever's left on the stack. Yeah.
What if the function leaves more stuff on the stack?
That's a great question. If the function leaves more stuff on the stack, then it is not a well-typed function, and it will not run. Yeah.
Oh, sorry.
Yeah.
Is there a floating point?
Yeah, there is a floating point. Actually, yeah, the what I said earlier about only i32s and i64s being on the stack, you can also have f32s and f64s. Yeah. But the Ethereum Wasm will not have floating point support, interestingly. Yeah, any questions? Yeah.
What are the globals?
Well, one of the main usages of globals, I'll go over this in a bit, is as a additional stack pointer. I'll mention why we need an additional stack pointer in a few slides. Yeah, but in addition, like if you have a global variable that happens to be an i32 or i64, it will go into a Wasm global, most likely. And if we want to call a function, we just push its parameters onto the stack. And after we've called the function, its result is now the top element on the stack. Right? Simple enough. Now, in order to actually access the parameters, this is a bit weird. The parameters are actually not on the stack when the function first starts running. They're placed into these things called locals. So locals are kind of like globals, except they're only scoped to the current function. So here we have a function that takes in 3 parameters. So parameter local 0, 1, and 2 are just going to be the parameters. And we declared a 4th parameter right here, which is local 3. And this one is just going to take our 3 parameters, add them together, and copy that value into this local variable right here, as well as return it. Yeah.
Why do we copy the value into local variables?
To demonstrate local variables. Yeah.
Not that.
No, they don't stay behind. This value would get immediately discarded. Yeah. And finally, we have loads and stores, which are pretty important. One thing that sets WebAssembly apart from other languages is that code is not actually part of memory. So you actually can't have function pointers, and you can't have indirect jumps because you'd have to have an address for this. So instead of having the code be a part of memory, each module gets its own address space, which is 32 bits, and it's initialized to all zeros. So when the module first starts up, all of its memory is basically zeros, unless it specifies some things to be initialized. The load instructions look like this. So here we have an i32.load8_s. This pops an i32 off the stack, which is the address. It loads an 8-bit value at this address, sign extends to 32 bits, and then pushes the result to the stack. Simple enough. So one problem that comes up with WebAssembly is that our stack can only hold i32s, i64s, f32s, and f64s. So we can't put buffers on the stack, which also means we can't put arrays or structs or any of the fancy language features that we've come to expect onto the stack. So basically, the only way to resolve this is instead of putting all of our stuff on the Wasm stack, we put it in a separate stack structure, which is typically called the C stack. So the C stack lives at the very top of linear memory, and it's pointed to by the first global. So the first goal was typically called the C stack pointer. So each time you want to allocate something on the C stack, you just subtract from the C stack pointer, and this new pointer that you get is now your is now the buffer that you've allocated. Okay. So this has a few interesting consequences, one of which is your return addresses are now stored in a different place than all of your buffers. So that's actually a really great security feature, because if you overflow a buffer, there's absolutely no chance that a return address will get overflowed. Of course, the C stack is not actually part of the WebAssembly language. It's just a quirk of compilers that generate WebAssembly. Yeah. We can have function pointers. And what happens if you compile code that has function pointers? You can't have function pointers directly, but there's a little array of function pointers that's separate from memory. And that's the only place that can contain function pointers.
Oh, okay.
And these function pointers are also opaque. And you can only call a function through this table of function pointers.
Okay.
Yeah. And it's called a function table. More on that later. Another thing that makes WebAssembly different is you can have if-else statements, which are just, the if-else statements that you know from your regular programming languages. One thing that is different, though, is your if and else blocks can actually modify the stack. So you can have an if block that adds an extra element onto the stack, which is then popped over here. Of course, your else block would also have to add the same amount of elements onto the stack as your if block. But that's one interesting thing for people who are coming from procedural programming languages. Right? Does that make sense to everyone? I should have had a separate slide for this, but yeah. If your else block doesn't do that, then your WebAssembly module is not well typed and it will refuse to run, which is a common theme among like WebAssembly. Like if any of your code isn't what the WebAssembly runtime expects, it will just refuse to run it, which is really great for security. Yeah, the whole module goes through a type checking process before it even gets run. And we also have block and loop instructions. Basically, if you can target a block or loop using br if or just br. And this number in this br if is the number of nested levels you want to reach. So in this case, you want to reach the one if block, which is, well, loop is the 0th level, so block is the 1st level. And you're targeting a block, which means when you target it, you want to reach the end. If you're targeting a loop, instead you want to reach the beginning. And actually this arrow is drawn incorrectly. Does this make sense to everyone? The integer here represents the nesting of the block that you're targeting. And if you're targeting a loop, you jump to the beginning. And if you're targeting a block, you jump to the end. Yeah.
So that's not for branch.
Yeah, that's a branch.
So if you didn't have a branch, it wouldn't have to loop.
If you didn't have a branch, it would not loop, which is it seems a bit strange, but we'll just allow it. Yeah.
Is loop different from block?
The difference is when you target a loop, you jump to the beginning, and when you target a block, you jump to the end.
Oh, okay.
Yeah. So actually, this BR could also mean like break if. I don't know. I don't know why they named it that. All right. Any questions on this? All right. So I also have another demo of just writing a WebAssembly function. So let's write a Fibonacci function, which is pretty simple. If n is less than or equal to 1, return n, otherwise return fib of n minus 1 plus fib of n minus 2. Right? Everyone agree with my Fibonacci implementation? So now we're just going to compile this using Clang. And the reason why I'm using Clang is because Emscripten adds all that, like, all of that garbage to my file and makes it 151 kilobytes. But if I pass in these parameters, no standard libraries, no entry, it will just compile just the function that I wrote. So now if you look at the wasm to wat of this fib.wasm file, I'm gonna switch back to my desktop where I have all of these set up. RDP. It's in my apartment. Okay, and then wasm to wat test.wasm. If we look at this, this looks a lot more manageable. We have this one function. We have this block. First, we get the parameter and we compare it to 2. If it's strictly less than 2, we branch to the end and we return 0. I don't know if this is correct. Oh, we return n. This is getting the 0th local. Otherwise, we grab n, we add -1 to it, and we call fib on n-1. Then we get n-2, we call fib on n-2, and we add the 2 results together and return. All right, can everyone make sense of this fib function that was generated? Okay. Okay, now let's write some HTML. That invokes this WebAssembly. And the previous HTML that was generated by Emscripten, that's like fine most of the time. You're going to want to adapt it based on your application, but I just want to show off how this is actually done inside the code. So we're going to have a script tag, which has some JavaScript in it, and this is where we will invoke our WebAssembly from. So first we have to use an async function. If you don't know what async function is, don't worry. It did not paste correctly. That's weird. I must have forgotten. That's even worse. Okay, let's open this set of slides inside of here. And let's hope this code works because I have not really tested it, TBH. Okay, now let's try pasting it in this last time. Oh my god. Oh wait, did I forget to save? Okay, I guess I did forget to save. Well, we're just gonna type in the stupid HTML boilerplate one more time. We have a head tag and a body tag, and we're gonna put our scripts in the body and paste it in. Okay, let's hope this works. And we have fib.wasm, which is, I believe, in here. Oh, I named it test.wasm. I'm gonna rename it to fib. And my function is actually called z3fibi, which is actually, if I compiled it using Clang instead of Clang++, I think I'll take care of it. Yeah, it's called fib now. Okay. This is the C++ mangled name of the fib function that I wrote. So now if we run Python 3-mhp server, and if we go to localhost, oops, and we open the console, oh, we get that the answer is 5, which I'm not actually sure if that's the correct answer. What did I call it with? I called it with 5. Wait, actually, that's definitely not the right answer. Wait. Oh, it is the right answer. 1, 1, 2, 3, 5. Okay, yeah, cool. Yeah, we did it. All right. And this was a pretty simple example. This module just generates this block of code. Okay. And we have our memory that's defined here. We have our function table, which actually has no reference, has no function pointers in it right now. We export our memory and also a bunch of global variables that we can actually access from JavaScript because we exported them. And for other use cases of WebAssembly, you can compile to WASI, the WebAssembly system interface, which allows Wasm to work outside the browser. So basically, this is a way for Wasm modules to make syscalls through the runtime. And I'm not going to go into too much detail, but basically know that you can compile to Wasm, run it in your console. You can run servers in Wasm. You can run games in Wasm, not in the browser. Basically, any program you want, you can compile it to Wasm, ship that Wasm binary, and run it anywhere you have a Wasm runtime. And because it is a virtual machine, you get nice isolation and security properties. So some of these security properties are, number one, control flow integrity. Pretty much all calls, actually every call, is well typed and statically verified. So you'll never come into a situation where you jump to a function and it's wondering what its parameters are, because the runtime will guarantee that when you jump to that function, its parameters will be well typed and well defined. In addition, every branch instruction is well structured. For example, if you weren't able to have that if statement which added a thing to the stack while the else statement did not, that would be avoided by the type checking procedure in the runtime. In addition, this one's a big one. Wasm is stack corruption resistant for the most part. And that's because the Wasm stack does not, which is the stack that contains return addresses, does not contain any buffers in it. What that also means is that there's no ROP, because any buffer you have is going to be separate from where the return addresses are stored. However, the C stack is not stack corruption resistant, so it's actually possible to overflow your stack variables if you have variables on the stack and also you have buffers on the stack. You can overflow into those stack variables. And in addition, we're not heap corruption resistant. So any database heap corruption should work. However, if you want to, for example, do like a counterfeit object-oriented programming attack that relies on replacing V pointers, you might be in a little bit of trouble because the V pointers don't actually live on the heap. What we actually have is a pointer into a function table, which then contains the actual pointers. And the function table is designed to be opaque, so you can't actually modify the function table itself using any WebAssembly instructions. So basically what this is saying is you can't replace a V pointer with any arbitrary value, but you can always replace a V pointer with another valid V pointer. And also the function that you're calling has to have the correct type. Yeah. Yeah, the C stack is on the heap. Oh wait, no. Well, it's a bit weird. The Wasm linear memory, which is the address space that's allocated for each each Wasm module is sometimes called a heap. But it's basically just a big array of bytes. There's actually a heap that's defined on top of that libc uses. So you have the heap like at the bottom of linear memory and the stack at the top of linear memory. So both the heap and the stack live in linear memory, but linear memory is also sometimes called heap. It's a bit weird. Yeah, you can call malloc and free because they're part of libc.
So, but I mean, when it's running in the browser, when it's running in the browser, the browser,
Wasm and C would be compiled as part of that 150 kilobyte Wasm file. So if we look at the Wasm to WAT of hello.wasm, okay.
when you call malloc, malloc is that memory.
Right, if we look at where malloc is input, oh, is it not in here? Well, that's annoying. Well, malloc is in here somewhere. For what? Yeah.
Running Wasm,
Some people say 80%, some people say 50%. And I say 40% if you're lucky. It's not great. But I mean, computers are getting faster, so asymptotically it's the same, so whatever.
I mean, it's about as bad as the improvement that you get from switching from JavaScript to Wasm.
Yeah, JavaScript is actually not fast at all.
Yeah.
But Wasm actually runs faster in Firefox, fun fact. Firefox runs JavaScript slower, but it runs Wasm faster. Because Google decided to use the same virtual machine for its JavaScript and WebAssembly. And I guess that means that its WebAssembly like runtime isn't as optimized for WebAssembly. Yeah. But here's some useful Wasm tools. There's Wasm time, which runs WASI binaries. If you ever want to write a server and have it run in Wasm. There's Wasm decompile, which is supposed to tell you what's inside a Wasm file, but this is not always super helpful. There's also Wasm to C, which takes a Wasm binary and converts it to a valid C file. So you can actually take your Wasm and compile it back to C, then compile it to some other machine code, and so on. You can actually compile it back into Wasm, and then compile that back to C, and yeah. Yeah, it gets worse every time.
Does it actually?
Huh?
Does it get worse?
Does it actually get worse?
Like if you go from Wasm back to
Yeah, it does.
Okay.
Yeah, because linear memory is implemented as a giant buffer.
Right.
So each time you access linear memory, you have to perform an address translation.
So it adds an extra layer.
Yeah. Yeah. All right. There's also a Wasm to WAT, which I've shown you guys before. And finally, there's a Ghidra Wasm plugin that takes your Wasm and lets you analyze it in Ghidra. That's pretty cool. You guys should check it out. All right. So that's the end of the talk. If you're not here in person, you're missing out on sushi. Huh? Yeah, that's fine.